I have a problem with the internet and the campus. You have same, right? Am I right? You have problem? Hello? Okay, yeah, same, yeah. So I use the hotspot with my handphone. Okay, so I do not use the video. Yeah, I turn off so to make smoothly. Yeah, online class. Now we have a new topic regarding with the semiconductor devices. That is the MOSFET. Yeah, MOSFET stands for metal oxide semiconductor field effect transistor. Sorry. Okay. Can you see my slide? Can?
Can, Doctor.
Yeah. So
Yes, doctor.
regarding the MOSFET, yeah. So we have now MOSFET. MOSFET stands for metal oxide semiconductor. FET. Yeah. Field emission transistor. Yeah. MOSFET is based on the junction between N, P, N. Yeah. So if I make the junction, yeah, we know that the junction is made on the silicon wafer. Yeah. In the first class, so we have yeah, introduced about the silicon wafer, where there so we can construct many semiconductor devices. Yeah. One of them is the MOSFET. So if this is a silicon semiconductor, yeah, silicon wafer, yeah, for example, yeah, this is silicon wafer. We have uh, this is uh, silicon wafer is a P-type, yeah, P-type semiconductor. Yeah, this is P-type. So we have a P, yeah, P semiconductor as a silicon wafer, and then we uh, develop the N-type. Yeah, so N-type is a we make this N-type here. Yeah, yeah, in this. So this is N-type, but the N heavily doped. Yeah. So this is we have N positive. This is we have introduced last time. I'm right. When we having the positive is heavily doped, whether we can dope with the hole or with the electron. Yeah. With the pentavalent element or trivalent element, yeah, to generate the hole or electrons, yeah, excess of hole or excess of electron. So this is we have a heavily doped. So you can imagine now this is a silicon vapor with P type of semiconductor, and we dop with the at a certain part, yeah, this part, yeah, with the rectangular, yeah, rectangular blocks, yeah, and this two, yeah, two location here, yeah, and this is a P, yeah. So this is the with the N type, yeah, N type in it with the uh, heavily doped, yeah, heavily doped. So heavily doped with the if N with the, for example, with the phosphorus, yeah, with the phosphorus. So we make heavily doped this, yeah. So why we use this heavily doped electron? Yeah, of course we want to have more electrons, yeah, in this design, in this construction, yeah. Okay, so we have a P here, and we have N, and we have N and with P. So we have a junction between N and P, and P and N. Yeah, we have a junction here. So then we can apply electric field, or we can apply voltage. Yeah, the electric field. So the name is a field effect transistor. Right? So the electric field is applied. So then the electron can move. Yeah, electron or hole can move, so then we can have the electric current, yeah, or the flow of electron, yeah. Again, I just remind you why we need the flowing of electron, because we want to energize the semiconductor, right? uh, we will make the uh, transistor, right? Transistor, the function, one of the function of the transistor is to magnify, yeah? So the current, yeah. So this is very important, yeah, in the devices, yeah, when we want to function the devices as a amplifier, yeah, to amplify electron, yeah, or current, then we need the transistor. Okay, so from this, then the we can develop further, yeah, develop further of the uh, uh, MOSFET, yeah. This is just illustration how to make NPN, yeah, junction, yeah. And then let make another, yeah, yeah, no good drawing, but I think to make yeah. Again, yeah, we have N, yeah, we have N here, yeah. We have N here, and then we have P here, and then uh, in order to connect, yeah, to reach to the resource of energy or battery, or we apply the electric field, then we will put the metal, yeah, we will put the metal, yeah, metallic, yeah, for example, yeah, we have this is N, yeah, we have N heavily doped, yeah, N type, heavily doped N type, and then on top of this we make a metal, yeah. So we connect with the metal here, uh, like this one, yeah. So metal, yeah. So this is a metal, yeah, on top of N, yeah. And then here also we have a metal, yeah, to connect with the uh, source of energy or battery, yeah, with the battery. So we have this is as a metal, yeah. We put the metal here, and then of course we have a terminal here. We have a terminal here. So this is the terminal. One of them is as a source, of electron, and other is a drain of electron. Yeah. So we suppose that there is the current flow, yeah, from the drain to source, or electron flow from source to drain. Yeah. So this is the uh, source and drain. Yeah. Gate of source and drain. Then we have uh, uh, so, terminal. I mean terminal, and then another terminal we put. Yeah. We have another on top of the P here. Aduh, tak bagus gambarnya, tapi oke lah. Yeah, so on top of this P, so we put the what is that? Yeah. On top of the P here, on top of P, we put the oxide here. This is oxide. Yeah, this is oxide. We know that the oxide is a what kind of material? Oxide is a insulator. Am I right? The insulator. So oxide is an insulator. Yeah, as an insulator. So what is the characteristic of the insulator? Insulator cannot flow the electric, cannot flow the electron. Am I right? So they can because there is no way in the insulator and the oxide that the current can flow. Yeah, because of what? Because there is no free electron there. There is no holes there. So all of the orbit are fully occupied by the electron. So then there is no space the electron to move from one crystal to another crystal. Yeah. So this is an insulator. Yeah. I will not explain more about this one, but we can understand. And then on top of the insulator, yeah, we have what? Yeah, we have here. Yeah. Yeah, we have a metal. We have a metal here. We have a metal. Again, we have metal, and then on top of this, we have a metal. Yeah, metal, yeah, or conductor. So we connect to the terminal. We call as a gate terminal. G. Yeah. We have discussed yesterday regarding with the what is that? Hot dog, hot dog transistor. Yeah, we call as the FET. Yeah, field effect transistor. Yeah, the simple field effect transistor is that we have discussed where gate. Yeah. Controlling the current of the drain and source. Okay. Now here, how can this MOSFET work? Yeah. So from this we have this is the length, yeah, between N and we have length L, yeah, and then we have on the bottom, yeah, on the bottom here we have a grounding system, or with terminal is a B, or we call as a base. Yeah. So this is we have a base, we have a G gate. Yeah. We have a source, we have a drain D. Yeah. So this is we call as a in this N, yeah, in the right side, so we call as a drain region. And then we have this is a source region. Source region. And then we have in between source region and drain region, we have this is as a channel region. Yeah, channel region. Yeah. Usually we call the channel, meaning the channel of flow of electron or flow of holes here. So then the current flow in this region, in the channel region. Yesterday also we have discussed regarding with the FET, yeah, or burger, or we call as a hot dog transistor, that in the channel region where the current can flow. Yeah, so the channel region in the FET we can control by increasing the VGS. Yeah, VGS is from the gate to the source. So then we can yeah we can expand the depletion region. The depletion region and can block the current to flow from drain to source, yeah, or electron moving from source to drain. Okay, so this is the now in the MOSFET. So how can it work, and how can we control the current flow? Yeah, so B is based on this we call body. We can this body connected to the source. Yeah, yeah, body or B connected connect connect, uh, connect to S. Yeah, and uh, connected to ground or grounded, yeah, system. Yeah, so S here and B are connected, so then we can like this, like this one. Usually we have a grounding system is like this one, meaning that we make this terminal to the grounding system. So the grounding system is a source of an electron. Okay, so then how can it work? Yeah, now we draw a cross-sectional in the cross-sectional view, yeah, in the cross-sectional view, yeah, cross-sectional view, cross-sectional. We can make this yeah, into the such a figure. Yeah, so if we see from the we can see from this view. View. Then we can draw the construction of the MOSFET like in this figure. Yeah. Yeah. So I should draw. So maybe you may follow and then to make more familiar with the drawing the semiconductor devices. Yeah. So this is N, yeah, in one side and N in another side. Yeah. Heavily doped N. So this is N positive. This is N positive. Yeah, heavily doped N. And then we have a channel region in the center. Yeah. We have this is a channel region. Channel region. And then on top of this, we have a metallic, yeah, source. Yeah, so this is metallic, and then we have a uh, uh, terminal. Yeah, this is S. Yeah, and this is D. Yeah, drain. Okay, and then on top of the P here, yeah, and this is a P. On top of P, we connect with the oxide. Nah, this is oxide. Yeah, oxide, and then on top of oxide, we have Yeah, this is metal. Yeah, metal. Okay. Yeah, metal plate. So we have over here uh, terminal G. Yeah. So we have this is a metal plate on top of oxide. Yeah, metal plate on top of oxide. Mm, yeah. So this is oxide. Yeah. So this we have this is oxide. Mm, yeah. And then this oxide, yeah, oxide can be SiO2. Yeah, can be SiO2. Yeah. I have made the nano fabrication of silicon oxide on silicon wafer. Yeah, you can see in my published paper. Yeah, on the nano fabrication of silicon on silicon dioxide on silicon wafer. Yeah, so I use the fabrication using the atomic force microscope when I was in IIUM last time. So I make this silicon oxide on silicon wafer. So this is the like we put, yeah, we manufacture or we develop the silicon dioxide on silicon wafer. Okay, and then so in this case, yeah. In this case, the gate, yeah, you can have the gate, gate G is completely isolated, yeah, isolated, yeah, uh, from the channel region, yeah. See here, E- G, yeah, gate G. This is metal plate, yeah, on top of the insulator, totally isolated with this channel region. Yeah, you can imagine, yeah, that we cannot flow the electron or hole through the silicon dioxide. Yeah, because this is a insulator. Yeah, so we isolated the moving of electron or hole. Yeah, what is the function? And later we will see what is the function of that one. Yeah, so then the grounded is connected to the source. Yeah, source, and this is a um, yeah, uh, and the body. Yeah, the base body. Yeah. Yeah, so this is a or and other we can give like this one. Yeah, this is we can connect, and then we make a grounding system like this. This is also okay. Yeah, you can make this is close to here as a grounding. Yeah, and it's here as a grounding as well. Or you can connect like this, and then with a grounding system. This is meaning that the source of electron. Yeah, ground is a source of electron, a negative charge. Yeah. Uh, so what happened? Yeah. If yeah, if we apply if we apply uh, the positive, yeah, positive charge or positive voltage, yeah, voltage to the gate, to the G, yeah. So if we apply the charge voltage to the G, then what happened? If we apply voltage, yeah, to the G here, wait a moment please. Any, oh, I thought that's need the admission to join, but oh, you have a question? I think so. Oh. Okay, you just respond. Okay. You may because I I cannot directly to read your message in the chat box. You can respond by opening the mic, yeah, unmute, and just yes, doctor, gitu. Yes, sir. Yeah. No, or you can interrupt with this. So then I can respond directly. Okay. Now we continue with this. Yeah. What happened with the G? Yeah. Uh, in the G here, uh, in the meta, we apply the voltage, or we apply the positive here. What happened? Is there any? So actually, what is the connection? What is the connection? Okay, I will draw again, so then will be clear. Yeah, uh, it's okay. Yeah, we have like this one. Yeah. So this is we have and 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 we have uh, and we have SiO2, and we have gate. This is S, this is G, and this is D. Yeah, and we have this is body, yeah, or B, or base. Yeah. So this is uh, we grounding, yeah, with a ground system, yeah, to the S and B. And of course, if we apply voltage, yeah, in the G here, I mean this is a positive. Where is the negative? Of course, uh, applying is like this one. Can this is positive, yeah, battery, and then negative to the ground system. Okay, so in this case, we apply the voltage to the G. Yeah. So this is can be to VGS or VGB. So also okay. So we have this is a voltage, yeah? VG, for example, VG. So what happened if we apply positive voltage to the gate G? Ada yang boleh jawab? Ini adalah we have this is a insulator. This is SiO2. SiO2. This is metal. This is a SiO2. So what happened when we apply the positive voltage in the gate? Ada boleh tahu? Boleh jawab? Saya kasih bonus satu.
Not sure, doctor.
Sorry?
Not sure.
Not sure. Okay.
Yeah.
Yeah.
I thought.
If we put the positive charge here, yeah, and then we meaning that we on the other hand, this is ground, right? We can like drawing like this one. Ground this is can be like this one. So meaning that we have a positive here and we have a negative here. Am I right? If you put this positive charge, this is negative charge. Yeah, you apply the electric field. Am I right? Because this is FET, right? Field effect transistor. What is the effect when we apply electric field? This is electric field from positive negative. So what happened? Yeah. So in this case, uh, ideally, if without any SiO2, so the positive charge, yeah, or hole can move, right? Can move to the P here, to the P. And this is N positive, this is N positive. To the P here. The P is a many hole, right? So many hole here. Many hole, many hole, many hole, many hole. Oh. If you apply, yeah, electric field to the GB here, yeah, then you will supply, yeah, the positive charge to the P. But what happened? You will not supply the hole, so the hole will be blocked by the silicon dioxide. Am I right? the hole will be blocked by silicon dioxide because there is no way, there is no space in the insulator. Yeah. So then the hole will stop here, will stop to the SiO2. And then what happened with this area? With this area, uh, of course, we have this is electric field. Yeah, we have the electric field here. Electric field causing what? Causing the attraction of electron on hole in a certain direction. For example, yeah, we have a negative here. Yeah, remember in the in the reverse bias. Yeah, if you connect P with the negative, so the hole in the P region will be attracted to the negative terminal of battery, right? But this is a big ground. Also, this is a resource of the electron, so they will attract the hole. But hole from the battery Fiji here will not pass through the silicon dioxide. That what happened? What happened then? So hole here will be pushed, will be attracted to the bottom side. So will be attracted to the bottom side to recombine with it, or will accumulate it at this end of this P region in this area. Yeah, so the hole will be here. And then what happened hole here? Hole near to the silicon dioxide. They will be pushed down. So then we can say if we apply positive voltage, positive voltage to the gate. Yeah. So so it will push push away holes 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 in the or below 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 SiO2 region, and what creating the creating the depletion, depletion region. Depletion region. Remember, depletion region. If we have you see here we have a P, we have N. If we apply the reverse bias like this one, remember, so negative will attract holes here, move away from the junction, so to the dead one. So there will be will be move away. So they will expanding the depletion region. So they increasing the depletion region. So meaning the depletion region is causing the diffusion from the further diffusion of electron from hole to the P. Electron from the N region to the P region, and the hole from the P region to the N region, and creating the space charge. Am I right? Space charge, right? Diffusion will causing the space charge, and the space charge will creating the electrostatic voltage, V0. If in equilibrium, but we have the reverse bias to the V0 plus, V here lah, Vs, for example. This is a Vs, Vs. So this is the creation of the depletion region here. Okay, but here also creating the depletion region, the hole will be pushed down, pushed down, and then will having the space here. And then what happened? We have semiconductor. Yeah, here intrinsic semiconductor, like intrinsic, because hole will push here to the down, and then we have a neutral semiconductor, and then uh, 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 depletion region is created by the moving of the electron from this to that, yeah, electron this to this depletion region. Yeah, why this moving here? We remember we have this is we have for example we have this we have the applying the voltage between drain and source, yeah, with the certain voltage, VDS, for example. Yeah, this is a we connecting here to S. Yeah, but it is easy to write with the grounding system. So we can imagine, oh, this is a can be say at the VDS. So we connect D and S. Okay, so this is a electric field created from the applying voltage in the D here, D positive, and S negative, of course. Yeah, so they will electron here will move into the depletion region, and then they will move here, yeah, without any restriction, without any constraint, yeah, without any blocking, yeah, because the electron will move here depending on the phi here, depending on the phi phi, yeah, in this D, yeah. So this is uh, the working principle of this construction. And then if we increase the phi here, phi ds increase, and then the electron will go here. And then what happened? Yeah, further increasing the phi ds, yeah, still yeah, in this channel, yeah, in this region, and then at the one time when the voltage of VDS a certain value, they will reach, yeah, the drain terminal, yeah, or in to the another uh, uh, heavily doped end, yeah, in the drain terminal, yeah. And then what happened? And then we'll so this is electron will move here, or in this case we can say that we have a current flow, yeah, current flow, yeah, here IDS, for example, yeah. Because of the creation of the depletion region uh, uh, as a because of the application of the positive charge at the G, and then pushing the hole to the body, to the base, yeah, and then creation of depletion region. And then when we apply the positive voltage at the D, yeah, to the S, where the all of this is the heavily doped N, and then the source of the electron can move here to the this region, and then the current or electron can go to the positive terminal of the battery, yeah, and then they combine. Or in other words, we create electric current, yeah, from D to S, yeah. So in other words, so we can create here, yeah, uh, channel. We have a current channel here, or a kind channel region. So we create the channel, yeah, below of insulator, yeah, dependence of the applying of voltage here. So how big the current flow here? Of course, dependence of the how big the VDS is applied. Yeah. So in other words, we can say this is a we have a variable resistor here, increasing the uh, VDS will increase the IDS. Yeah. So this is as a variable resistor. Okay. This is the principle of work, and then we can drawing again, yeah, and then with the explanation. Yeah. So we have a better drawing. Yeah. 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 And happily dot n, and we have SiO2, and we have this is S terminal, and this metal and D terminal, and then we have another G terminal. Yeah, yeah. G terminal. Yeah. So and we apply the this is a positive. Yeah. G, and then we have grounding. Yeah, here with the body here. Yeah, and of course we grounding. Yeah, grounding the body and B. Okay, and then this is also we grounding the S. Yeah, and we have here, yeah, we have ID or IDS, yeah, because this is to the S, yeah, ID, and then we have push down, yeah, the push down the hole, yeah, push down the hole, yeah, 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 hole, yeah, and then the creating, yeah, the channel here. Yeah. So in this case here, so this is initially yeah, created uh, yeah, channel region. Yeah. Initially created channel region where the current flow or electron moving here. So this is the when yeah, this created, yeah, initially created channel region. Yeah, of course, if we push down the H is a small amount, of course there is no maybe a current and here will you see will uh, uh, recombine with the whole here. Yeah, but when we push down again with the increasing the G here for the positive here, and then will be there is the enough channel region, yeah, enough channel region to allow the electron from S to drain, yeah, yeah, electron from S reach the drain terminal, yeah. So that that's a condition, yeah, that condition the initially created channel region after uh, VGS, yeah, VGS, this is VGS, yeah, we apply the positive terminal in the G, yeah, and the S, yeah, as a ground, yeah, greater, yeah, or same as a threshold, yeah, threshold voltage where the channel region created, yeah. So then meaning the creation of the channel where the electron from the S can reach to the D here, yeah. So this is a we call as a threshold, yeah, threshold yeah, voltage. Okay. So in this case, we have a so-called we have a variable, yeah, variable resistor, variable resistor, because we can have a if we yeah draw yeah VD to the ID, yeah, so they will be increased like this one. So this is a variable resistor. Yeah, we know that the R equal V, yeah, over I, right? So if we did this I, yeah, increasing the V, and then increase the we have increase the R as well. Yeah. Okay. So this is the we call as a variable resistor. And then further analysis for this one. So what happened? Yeah. Yeah. So this is when the variable we have a we have a variable resistor. Um, of course, between uh, drain and source. So in this case, yeah, if we can analyze if VGS, yeah, greater or same as a threshold voltage, and yeah, uh, yeah, VDS, yeah, DS, yeah, greater same as zero, VDS, yeah, yeah. So this is a zero. Of course, there is no current flow here. There is no electric field from the S to D. Am I right? Then, if the VDS also small or same as a VGS minus VT, yeah, threshold voltage, yeah. So this is a all equal to the uh, uh, overdrive. We call as a overdrive. Sorry, overdrive voltage. Yeah, overdrive voltage. Yeah. So this is a overdrive voltage when the channel created. Yeah. Uh, VOV equal overdrive voltage. Yeah. So in this case, the VGS, yeah, uh, control control the area of the channel. Yeah. Yeah. See here, yeah, VGS, yeah, or VGS, yeah, can be this is a we call a VGS equal, yeah, VGB, yeah, same, yeah, yeah, GB, kan, because this is S and B grounded, right? So this is if we increase the VGS or VGB, so they will more push down the hole, and then we created more depletion region, and then we created the more space for electron, yeah, to create the channel region. Okay. So that's why this VGS or VGB, yeah, VGS or this is, can be VGB, yeah, can be VGB, controls the area of the channel, yeah, area of what? Area of what depletion region or area the channel region. Okay, and then in this case we have a variable resistor. Yeah, so we can also from the this operation, so we can determine the conductance. Yeah, uh, drain to source. The conductance is uh, symbol by G, small g, and we have a CDS equal 1 RDS. Yeah? R is a resistor. Yeah, resistor. So then we can have a K and VGS uh, minus PT minus half of VDS. Yeah. So this is a VDS. So this is we can determine as a half of a VDS. Yeah. VGS minus PT minus half of VDS. Multiply the constant. Yeah. So this is the conductance, and then we can have a current. Yeah. The current. Uh, yeah, drain to source, yeah, as a we have a ID, yeah, ID equal Kn, yeah, Kn is constant, VGS minus VT minus half of VDS, yeah, uh, multiplied by VDS, yeah. So this is ID. Okay. Yeah, of course, this is the same as a ID as a VDS over RDS lah. Yeah, so this is the ID. Yeah. So this is the MOSFET, and then we can have the characteristic VI over MOSFET. In this case, we have this is VD, VDS. This is ID. Yeah. And then we have yeah. So this is the equal, yeah, overdrive voltage. Yeah. So this is the here until here, yeah. In this point is the VOB, yeah. Yeah. This 8 peak, 8 peak at the VDS, yeah, equal VOB. Yeah. So this is maximum. Okay. Yeah, and then we can later we can have the characteristic later, yeah, for the further, yeah, operation, yeah, later we have operation where the triode mode, yeah. So this resistive operation of the one of the operation of the transistor where we call as a triode mode, yeah. So that we have this is a certain VGS, yeah, VGS1 for example, and then we have VGS2 for example, yeah. So this is a external, yeah. So this is we call as a triode mode, yeah. Okay, I think time is off, yeah. Time is up. So we end this class. Yeah, I hope that you understand. Yeah, in this principle work on the MOSFET. Yeah, and before that we have a BJT, bipolar junction transistor. We have the basic of the hot dog transistor or FET transistor. Yeah, field effect transistor. Okay. So this is we stop, yeah, until this. We have 1 hour because you have attended the sharing session from the guest lecturer. Yeah. Okay. Oh, we have test, yeah, midterm test after break. So the break is changing, right? Next week, right? 1 week. So after a semester break, mid semester break, yeah, we have a test. Yeah. So I will post, yeah, what is the important to study, yeah, for the test, yeah, for the after break, yeah, maybe on, yeah, soon, yeah, on Tuesday, yeah. Tuesday is what date is that? 30, yeah, 30 November. Okay, and on 30 November we have a test, and then I will post what is the important topic that you are going to study. Okay, to highlight. Okay, any question, brother, sister?
No, Doctor.
No, Doctor.
Okay, ya, jelas ya. So I will put this recorded video, yeah, in column or in the YouTube, so you can watch, yeah, much more to make more understand. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr.
Okay.